In this video, I want to talk a little bit about inductors and the properties of real inductors and how they differ from the ideal inductors that we use in simulation models. It's worth noting that inductors are by quite a long way the least ideal real components that we will meet in the lab. It's always a good idea to avoid using an inductor if at all possible. If you can design a circuit which needs to be frequency dependent, but which uses capacitors rather than inductors, then you will find your design task much easier. The equivalent model of an inductor looks like this. This is a typical model used. The inductor itself is there. There is what can be quite a large series resistor there, and an overall parallel capacitance here. And instead of the dissipation factor that's often used to characterize capacitors, inductors are often specified in terms of a Q value. And the Q factor is almost the exact inverse of the dissipation factor used to specify capacitors. The Q factor here is the reactive impedance divided by the real resistance. So it's the value of j omega L, or the magnitude of that, divided by Rs, the size of this parasitic resistor there. And that resistor can be quite substantial. Real inductors tend to have a large number of twists of the wire around the central core. And in order to get them in a physically small body, you need to use a very thin, narrow wire. And that means the wire has quite a high resistance. And with quite a long length of high resistance wire, that series resistance there can get significant. It can easily be tens of ohms. What's rather more concerning, and which doesn't really fit into this model that well, is that resistor tends to be a function of frequency as well. And it's a function of frequency in a way that cannot easily be represented by a set of discrete components like this, because its value tends to increase as the square root of the frequency, due to something called the skin effect. Now, inductors tend to be used at fairly low frequencies, frequencies where the effect of this parallel capacitor can be neglected, so we're really only concerned in terms of the parasitic components of an inductor with the value of this resistor Rs. And the Q factor there will be specified in the datasheet of the inductor. Plotting the complex impedance of the inductor on an Argand diagram like this produces this type of result, with the real component being the parasitic resistor and the imaginary component being the impedance due to the inductor that we want. That there would be the complex impedance of that inductor at the frequency that is specified. And in the case of an inductor, it's really important to specify the frequency because the value of Rs, the real component of the complex impedance, is also a function of frequency. You can derive the value of Rs from measurements in the labs. For example, supposing we determined that the voltage across an inductor was 3.3 volts peak to peak, and the current was 50 milliamps peak to peak, and the voltage leads the current by 72 degrees. Then we could represent both the voltage and the current in terms of their phasor representations. If we use our voltage as our reference phase, then we would represent the voltage phasor as being just 3.3, and that would be a real 3.3. Would appear there on the Argand diagram at 3.3, real imaginary, and that's 3.3 volts. Our current phasor, that would be 50 milliamps at a phase angle of, well, if the voltage is leading the current, then the current would be somewhere down here, 72 degrees in this case, behind the voltage, and it would have a value of 50 milliamps. That's its amplitude. So that point there would be 50 milli times e to the power of j, and minus 72 degrees is the angle. Right, well, the complex impedance is just the phasor representation of the voltage divided by the phasor representation of the current. So that would be 3.3 divided by 50 milli e to the power of j, and it's minus 72 degrees. I should have added that up here as well. That's a fairly simple sum to work out. 3.3 divided by 50 milli. Oops. 66 times e to the j, 72 degrees. Now, that is a total complex impedance of our real inductor. It has a real part and an imaginary part. And if we use the model of the inductor, that it's an inductance in series with a parasitic resistance, then the total impedance of this network must be j omega L plus R. In other words, the real component of this complex impedance is R, and the imaginary component of this complex impedance is j omega L. So if we just work out what the real and imaginary components of this complex impedance are, well, that would be 66 times cosine of 72 degrees is the real component, 20.4, and the imaginary component would be j times 66 times sine of 72 degrees, 62.77. So we can see from here that R, or RS, our parasitic resistance, is 20.4 ohms, and omega L is 62.77 ohms. So if we know omega, and we can see that this measurements were taken at 1 kilohertz, so omega will be 2 pi times 1000, our L, 62.77 divided by 2000 pi, the value of the inductance in this case, as near as makes no difference, to 10 millihenries. So this looks like a 10 millihenry inductor with a series resistance of 20.4 ohms. And that's the model that we would use for this inductor. However, do be aware that these resistances here, these parasitic resistances, do tend to be functions of frequency. Now, at higher frequencies, when you cannot make the assumption to neglect the parallel capacitor, the effect of the inductance tends to look something more like this. At low frequencies, well, at very low frequencies, it's dominated by the value of RS. Because the inductor is having almost no effect, the frequency is so small, the total component is really just determined by the value of RS. But as you see, it's not exactly constant. The value of RS does tend to increase slightly with frequency, until you get to the point here where the value of the inductance, or the impedance due to the inductance, starts to dominate the impedance due to the resistance. And over this range of frequencies here, the component is behaving like an almost ideal inductor. Until you get up towards a resonant frequency, where the effect of the parasitic capacitor starts to play an important role and starts to counteract the effect of the inductance. And at a particular frequency, known as the resonant frequency again, the impedance of the component has a maximum. Above that point, the impedance of the capacitor is smaller than the impedance of the inductor and the resistor in series. Most of the current flows through the capacitor rather than through the inductor part of the model, and the component starts to behave like a capacitor. And these are values taken from a real inductor datasheet. Note there's only really a quite small range of frequencies, a couple of orders of magnitude of frequency, in which you can assume that the inductor is behaving like an ideal inductor. Now, final thing that I have to warn you about real inductors is that most real inductors have an iron or ferromagnetic core to increase the magnetic field inside the inductor itself in order to give a bigger value of inductance in the same physical volume, just like capacitors use dielectrics. However, in the case of inductors, the problem is that the magnetization field, the extra magnetic field generated inside the core, is not linearly related to the external field. And that results in the fact that most inductors do not behave like linear components. Double the current flowing through them, and you do not double the voltage across them. It's just another problem you have to deal with when designing with inductors. Summary of inductors: don't use them unless you absolutely have to. They are a bit of a pain.